The intent of this video is to give you the basic outline of the concepts involved. So in that regard, I'm not going to go into the details of derivation and calculations of math involved. Okay, let's start from something very small, the simplest quantity you can ever imagine, a number, right? It is a single value. Say for example, you have 5 or minus 3.5, some value. I'm just putting some numbers. So this is a scalar. Okay, in physics, a scalar is just a magnitude. It does not have any direction. Say for example, like temperature. When you talk about temperature, it will have 30, a scalar value, and the unit involved. So basically, degree Celsius. Okay. When you talk about speed, 60 is a scalar value, and you have the measuring unit, kilometers per hour. Okay. So this scalar has magnitude but does not have any direction involved. But the moment direction becomes very important, like if you want to say the force, if you want to represent the force applied in which direction, that's the question, right? So in those cases, like velocity representing velocity or force, you enter the world of vectors where direction is involved. So in physics, as I said you, this vector is represented as a quantity which has magnitude and direction. Okay, you can say it's like you're walking at 5 km per hour in each direction. So it has both the quantities. Okay, in mathematics, we basically represent vector within square brackets, or you can tell it is a group of scalar. So when you have multiple rows, you call it as a row vector. When you have multiple columns, you call it as a column vector. But basically, it is just a single dimensional array. Okay. For example, let us take 3, 4 in a 2D space. 2D space means we have the x-axis and y-axis. So this 3, 4, what it represents? It means we are going 3 steps in x direction and 4 steps in y direction. Okay, so the length of the arrow will give you the magnitude. So basically we represent v, this vector with the symbol of v, and we have a right arrow above v. So this is how basically it is represented. Okay, now in data science, think of each row. So basically in data science what we do is we want to represent the data sets. Say for example, you want to represent the student database. Okay, so each row will have information about each student. So column basically will represent the features. So in this case, what will be the features? So student name, their height, their information, their marks, their discipline, etc. So these are basically features. But you should note, these are not anymore one-dimensional vectors. It is a group of vectors, you can say. This is exactly when you come across the term called matrices. So far we have learned what is scalar, what is vector, and slowly we are approaching what is matrices. Okay. Now, actually, when you get into the terminology of matrices, is exactly where you are getting into multi-dimensional space, where you have multiple row of students. Say, okay, you have many students and you have many features. So actually, it is a high dimensional. Obviously, it is a high dimensional space, right? Okay. Having said that, now, what is linear algebra, or why this linear algebra actually? Why all these concepts are coming under linear algebra? What is it exactly? Okay, So when multidimensionality comes in picture is exactly when you need the help of linear algebra. I'll tell you why. What if you have hundreds of students, or maybe thousands of students, and features possibly thousands to 10,000s of features? So you need some mathematical language to represent and process it, right? So this is where linear algebra helps us to do the operations. Okay, what kind of operations? Like adding vectors, maybe you can scale them, you can rotate them, transform them in a geometrical representation. Okay, and also it introduces the idea of matrices, grids of numbers, matrix that can be seen as a transformation machine. You feed into a vector, stretches it, rotates it, flips it, etc. Okay, but more than that, matrices helps us structure and operate on large scale data effectively. Okay, so matrices are of versatile benefits to the data science or mathematics or physics. So because you are dealing with multi-dimensionality data. So every image, when you talk about data science or machine learning, or you can specifically say OpenCV. Okay, so if you want to represent an image, every data set, every transformation in AI or computer graphics, underneath it all is the linear algebra doing the heavy lifting. Okay, so as the dimensionality increases, things are getting complicated, or you can say things are getting even more interesting. We now have a bunch of data. Say for example, we have 100 features. Basically you can take it as a column per point. Okay, so it becomes impossible, right, to see all this 100 dimensional space, all these features in the geometrical representation, or graphically you can call it. This is where things are getting more interesting, I would say. Not all features, I said you have 100 features. So are these 100 features contributing to equally? No, right? Some are noisy, some features can be noisy, some features can be redundant, some can be not of not much importance. Imagine data points being spread widely in one direction, and you have some other direction wherein the data spread is relatively shorter in length. So you can say that the first one, where the data is spread in a wide range of spread, where there is a wide range of spread, has more information. Okay, this is where the concept of eigenvectors. Okay, now learners, there is two important concepts which gets much interesting: the eigenvectors and eigenvalue. So first I would like to say, what are eigenvectors? These are like a special vectors where when a matrix is acting on them, they do not change the direction. Okay, listen carefully. This do not change the direction, only the magnitude, that is the size of the vector is changed, not the direction, which basically means it can be stretched or compressed. Okay, so and now we know what is eigenvectors. Now what are eigenvalues then? They tell you how much the direction is to be stretched. Okay, so basically this is telling how much you should stretch or how much you should compress. So in data science this is becoming very powerful. This has already become very powerful, and which is useful in matrix decomposition, PCA, principal component analysis, and SVD, single value decomposition. So basically these eigenvectors and eigenvalues are a set of mathematical operation done on a multi-dimensional matrices, where after performing several steps we come to a point of reducing this multi-dimensional matrices to a low dimensional matrix. Say for example you had 100 features for 100 students. So basically 100 cross 100, right? 100 rows and 100 columns. But now we are telling that 100 features are not necessary. These eigenvalues and eigenvectors are making you reduce this multi-dimensional matrices to a two-dimensional matrices. So the idea powers image compression, facial recognition, noise reduction, topic modeling, and even genomics. So these are the fields which uses this PCA. Okay, in essence, PCA helps us answer the question what really matters in this data. So it is bringing you clarity, direction, and efficiency. Okay, so the next time you see a data set with the dozens of columns, think which direction really matter. Where does the data actually live? In which direction does it living in abundance? That is where actually the meaning holds. And other data are not much required. And how I can rotate my perspective to truly see where the data is widely spread or where the data is living. That is the power of linear algebra. And so that's it. Let's keep it simple. So let's wrap up this session. Okay, so this is Lakshmi from the Sciverse. Thank you.